Let's talk about significant figures. These are a system that scientists have come up with to talk about precision of their measurements. It tells us how precise a measurement is. So how does it do that? Well, let's see, okay? First of all, we also call significant figures as sig figs in short, or sometimes they're also called as significant digits. They're all the same thing, okay? And secondly, most importantly, significant figures is a system that only applies to measurements. Remember, we're talking about precision, and the idea of precision only applies to measurements. What kind of measurements? Well, any measurements that you and I do in our daily life or in labs, or the ones that scientists do. Any measurement you take, the system applies to them. But it does not apply, or it's not needed for exact quantities. For example, consider the number of students in a classroom. Okay. Now, if you have 5 students in a classroom, that's not a measurement. That's an exact number. So the idea of precision doesn't come over here because you're not using some kind of a measuring tool to, measure it. It's not a measurement. So significant figures does not apply over here. Same is the case for if you're counting the number of eggs, for example, or if you consider the price of a chocolate bar. Again, look, it's not something that's measured. All right. And that's why we usually don't talk about significant figures in our daily life, because a lot of times we're talking about these exact quantities. It's a system that only applies to measurements. Okay. But the next question is, how many significant figures are there in a given measurement? All right. That's what we're going to talk about in the rest of the video. And for that, we have a few rules. There are 5 of them. And so that's what we need to learn. We have to memorize them, unfortunately, but we'll try to do it step by step so it sounds intuitive. So let's talk about the rules for determining the number of significant figures in a given measurement. So here's how I like to think about it. If you take any digit of a measurement, it can either be a 0 or a non-zero, isn't it? So let's look at them separately. So let's start with the non-zero. What's the rule for significant figures when it comes to non-zero digits? Well, the rule is actually quite straightforward. All non-zero digits in a measurement are significant. Done. So let's see what that means. Let's take an example. Consider a measurement which says 7.2 centimeters. How many significant figures are there over here? Well, we have 2 non-zero digits over here, and they're both significant. So there are 2 significant figures. Done. Okay, let's take another measurement. How many sig figs do we have over here? Remember, sig figs is a short form, okay? How many do we have here? Well, we have 3 non-zero digits, so there are 3 sig figs over here. What about this one? Ooh, there's a decimal point, but that doesn't matter for us. All non-zero digits are significant. So 1, 2, 3 again, 3 sig figs. Clear? All right, so all non-zero digits are significant. What about the zeros? Ooh, that's where it all gets interesting, actually. Okay, now zeros can appear in many places in a measurement. For example, take this big measurement, okay? You can have zeros in the front of the measurement. We call them as leading zeros. You can have zeros in between non-zero digits. And you can also have zeros at the end of the measurements. We call them trailing zeros. Now, guess what? The rules are different for each one. So let's look at each one separately. Again, let's start with something simpler. Let's start with the zeros that are in between. The rule for them is that all zeros between non-zero digits are significant. So let's take more examples. We're going to take a ton of examples, okay? So let's take an example. Let's consider this measurement, okay? How many sig figs are there over here? Well, first of all, we know that these 3 are significant because they're non-zero digits. They're all significant. Then we have a 0 in between 2 non-zero digits. And we know that all zeros in between non-zero digits are significant. So this also becomes significant. So we have 4 sig figs over here. Okay, what about this one? Well, again, we know these 2 are significant because they're non-zero digits. And all zeros in between non-zero digits are also significant. So we have, these 2 are also significant. Therefore, again, we have 4 sig figs. All right. So all zeros in between non-zero digits are significant. What about the zeros which come in front of the measurement, the leading zeros? Well, the rule for them is that all leading zeros are not significant. This is where things start to get interesting now. So let's slow down a little bit. Let's take some more example. Consider this one. Okay. So how many sig figs do we have over here? We'll always start with the non-zero ones. That's easier. So I know that these 2 are significant. What about this 0? Remember, all leading zeros are not significant. This is a leading 0, a 0 in front of the measurement. That's not significant. So there are only 2 sig figs over here. Okay, what about this one? Why don't you pause the video and try? Okay, here goes. We know this and this, these two are significant. We also know a zero in between two non-zeros is also significant, but this is a leading zero. Leading zeros are not significant, which means this measurement has 3 sig figs. Let's take another one. How many does this have? Well, this one is significant. And look, these both are leading zeros. They're not significant. And therefore, this measurement has only 1 significant figure. Now, at this point, we might have a few questions. So let's dig a little deeper into this. So the first question we could have over here is, if these zeros are not significant, could I just get rid of them? Could I just write this as 0.5 meter, for example? And the answer is no. These two are definitely not the same. They're not the same numbers, so they'll not be the same measurements. They are definitely not the same. When we say they're not significant, what we mean is that they don't add to the precision. That's what we mean by it, okay? So clearly, you can't get rid of them. That's wrong. Okay, another question we could have is, why are these leading zeros not significant? To answer that question, let's try to express this measurement in a different unit. Let's say in centimeters. 0.05 meter is 5 centimeters. When I express it in centimeters, look, I get only 1 digit, 1 significant figure. The zeros go away. Now, if these zeros were significant, then expressing measurements in different units would change the number of significant figures, would change the amount of precision. That doesn't make any sense, right? And that's why these zeros are not significant, because you can get away with them by just expressing them in different units. Another way to get rid of these zeros is by expressing it in a scientific notation. So for example, you can write this as 5 times 10 to the power minus 2 centimeters. See how these leading zeros go away? That's why they are not significant. They don't add to the precision. They're just placeholders. By the way, when we are working in scientific notation, only the significand, that's what we call it, significand, it ends with a D, okay? This is the only one that has significant figures. The exponent and the 10, that does not have any significant figure. So over here, there's only 1 significant figure. Here's another measurement in scientific notation. How many sig figs does this have? Well, if you look at the significand, there are only 3. So there are 3 significant figures, 3 sig figs. The 10 and the exponent over here does not count. Okay, let's try one more. How many sig figs over here? Well, let's see. We know these two are significant. We know the zero in between is significant. And all the leading zeros are not significant. So there are 3 sig figs over here. And again, we can express it in a different unit, and we can see we get rid of those zeros. Or we could just write it in the scientific notation. Okay, that brings up the last question. What about the trailing zeros? And this is where it gets even more interesting, because the rule is all trailing zeros are significant if there is a decimal point. Okay, let's look at some examples over here. So consider this measurement. How many sig figs do we have? Well, we know these two are significant. And then we have a trailing zero, a zero at the end of the measurement. Now, if there is a decimal point, then all trailing zeros are significant. We see a decimal point, so this is significant. So there are 3 sig figs over here. But why? Why is this zero significant? Well, let's see. Let's compare it to a measurement which is 3.1 grams. We already know that in any measurement, the last digit is an estimate. So over here, this 1 is an estimate. So we have very little confidence in this 1. But over here, it's the 0 that is an estimate, which means we have a lot more confidence in this one. So you can see 3.10 grams is more precise than 3.1 grams. And that's why the trailing zero matters. When there's a decimal point, it adds to the precision, and that's why it is significant. Now consider these 3 measurements. How many significant figures each one has? Well, over here, there are only 2. Here, well, this trailing zero, the 0 at the end of the measurement matters. It's significant because there's a decimal point. So there are 3 sig figs. And over here, there are 4 sig figs. It makes sense because this is more precise than this one, which is more precise than this one. So for a given measurement, you can see more the significant figures, more is the precision. Okay, one more example. Why don't you pause and try? How many sig figs over here? All right, so we know these 3 are significant. We know the zeros in between the non-zero digits are also significant. And now we have a 0 at the end of the measurement. If there is a decimal point, they're all significant. And so all digits are significant. So there are 7 sig figs over here. So the ultimate final question is, what about trailing zeros if there isn't a decimal point, right? That's the last thing. Well, it turns out the rule is if there is no decimal point, trailing zeros are not significant. How does that make any sense? Well, this rule exists because we humans love to round things off. For example, when we say the distance between two cities is 2,500 miles, we don't mean it's exactly 2,500. We have rounded it off, isn't it? So these zeros are not really adding to any precision. Similarly, if we say, a swimming pool has 20,000 gallons of water, we don't mean exact 20,000. It's a rounded off number. That's why these zeros don't add to the precision. And that's the reason why if there's no decimal point, the zeros do not count. Okay, so let's look at some examples over here. How many significant figures in this measurement? Well, I know that this is significant and I have trailing zeros, but I don't see a decimal point. If there is no decimal point, they are not significant, and therefore there's only one significant figure over here. But wait a second, what if we are not rounding things off? What if we measure something to be precisely 3,000 grams, for example? Now what? Now these zeros are adding to the precision. Right? So how do we express it in a way that people understand that we mean business over here? Well, the simple way is to just add a decimal point, because when you add a decimal point, the trailing zeros become significant. We saw in the previous rule. But how do you add a decimal point? Well, there are a few ways to do that. Well, the best way is to write it in scientific notations. And in the significand, write it as 3.000. This will make sure that all these zeros are significant. There's a decimal point, so the trailing zeros become significant. But another way is we could express it in a different unit altogether. For example, 3,000 grams can be written as 3.000 kilograms. So again, we are adding a decimal point, so the trailing zeros become significant. Okay, another way, which is not very common, but you can do that, is you can just add a decimal point at the end of the measurement. And the moment you add a decimal point, the trailing zeros become significant. But I think that writing in scientific notation is the best way to do that, because suppose we have, again, a measurement of 3,000 grams, but this time we want to express that only this zero is significant and not these two zeros. It's precise up till this point. How do we do that? Well, the best way is to write it in terms of scientific notations, and this time let's only include one zero in the significand, so that this way you have two significant figures. And there you have it. These are the 5 rules for determining the significant figures for a given measurement. Okay, now that we have these rules, let's apply them. Feel free to pause this video and try to find the number of significant figures in each of these measurements. Okay, let's begin. So the first one, all non-zero digits are significant. So there are 3 non-zero digits, 3 significant figures. Okay, what about this one? Well, I know that non-zero digits are significant. There are 3 of them. And this 0 is in between 2 non-zero digits. So that's also significant. So all 4 are significant, giving you 4 significant figures. Okay, what about this one? Well, we know that these 2 are significant. And we know this 0 in between these 2 are significant. But the leading zeros are never significant. So that means there are 3 significant figures. What about this one? Well, we know these 2 are significant, and trailing zeros, if there is no decimal point, they're not significant. The whole idea is that this represents a rounded off number. So these don't add to the precision. Therefore, there are only 2 significant figures. What about this one? Well, we know these 2 are significant, and the 0 in between these 2 are also significant. Does it matter that there is a negative sign? No, that doesn't matter. And the 10 and the exponents, they don't count. So there are 3 significant figures. In fact, when we write in a scientific notation, the significand will always have all digits to be significant, okay? Okay, what about this one? This is a good one. Well, 23 pieces of bread is not a measurement. It's a count. It's an exact value. So this was a trick question. There's no concept of significant figures over here, okay? Okay, what about this one? Well, I know that this 7 is significant, and leading zeros don't count. Leading zeros are never significant, and therefore there's only 1 significant figure. What about this one? Well, I know this is significant. Then there are some trailing zeros, and then there's a decimal point. The moment there's a decimal point, all trailing zeros become significant. So there are 5 significant figures. What about this one? Well, I know this is significant. Then there's a decimal point, so the trailing zero, the 0 at the end of the measurement, is also significant, but leading zeros are never significant. So these 2 are significant, so there are 2 sig figs over here. Finally, what about this one? Well, I know these 2 are significant. The trailing 0 at the end of the measurement is also significant because there's a decimal point, so there are total 3 sig figs. Remember, these don't count.